All right, folks, today we're continuing to build on what we talked about in Chapter 11 with autonomous differential equations. Now we're going to generalize to the idea of systems of autonomous differential equations, which just means more than one equation. And you can see a system here where the independent variable is t, and the dependent variables are x and y, which means x and y are both functions of t. And what makes this autonomous is that the right-hand sides of these DEs don't involve the independent variable t. They only involve the dependent variables x and y. So for example, if I had the differential equation like this, that's an autonomous differential equation, but if I added t in there, then it's not autonomous anymore. So we're only considering the ones that don't involve t's explicitly in the right-hand side, although x and y both depend on t. So we talk about the solution of this system literally being the two functions x and y that depend on t. And typically we need initial values, right? We need to start x and y somewhere, and then these equations tell us how they change with time. So at some particular moment, typically t equals 0, we're given the initial values x sub 0 and y sub 0, and then this tells me how quickly x is changing, so I use that to start stepping x forward, and this tells me how quickly y is changing, and so I build the solutions that way. The other idea that we have, and we talked about this earlier as well, is the idea of an equilibrium point for this system. And in this case, it's a point xy that creates a zero rate of change for both x and y. In other words, these two functions are zero. So x is not changing, so the f function is 0 over here, the right-hand side is 0, and y is not changing, so the rate of change of y, that was g, that's equal to 0. And so this is very similar to what we've talked about already. Let's see an example. So here's two differential equations, dx dt, dy dt, and they're autonomous because there's no explicit dependence on t on the right-hand side. So giving the differential equations is essentially just giving the functions, f and g. So in this case, if we want x not to be changing, then we need the quantity minus x plus 1 to equal 0. And so in that case, x must be 1. And if we want y not to be changing, then we're going to have the equation 1 minus 2y is equal to 0. And solving for y, that gives us 1/2. And so this autonomous system of differential equations has the equilibrium point 1/2, right? They're the xy values that make x and y unchanging, because if I plug those values in for x and y, the rate of change of x and the rate of change of y are both 0. So let's use those ideas and this example, and we'll build an idea of what the solutions look like. So we're going to build graphically the solutions of this differential equation system. So here's our differential equation. We've got the equilibrium point, and I've marked the equilibrium point on the picture here, and I've kind of sketched in the dotted line where y is equal to 1/2 and where x is equal to 1, right? And where x is 1 and y is 1/2, the rate of the equilibrium point is right at the center, and so the x and y's don't change if I'm sitting at that point. So if that was my starting point, remember we talked about initial values, if my initial value was 1/2, in other words, I started sitting on this point, then I would stay there for all time because the rates of change of x and y is 0. X isn't changing, so I don't move left or right. Y isn't changing, so I don't move up or down. So that's what the equilibrium point's giving us. And the picture here is called a phase plane. And it's called the phase plane because I'm not showing time, right? The independent variable here is t, and I'm not showing t. I'm showing x and y. So they're the dependent variables, but often it's a more useful way to think about those dependent variables. And we'll come back to what the time means in a second. But let's imagine for a second that x is equal to 1. Imagine we're on this, and I haven't filled that in, imagine we're on this line, x equals 1. What's happening to x? Well, x isn't changing at all. So if I'm sitting at a point like here on the line, or a point like here on the line, then if x is 1, x isn't changing. So if I start sitting there, then I don't move left or right, because x changing would be going left or right. So I'm not allowed to do that. X is not changing, so I'm not allowed to move left or right. But thinking about what's happening to y, if I'm up at this point, maybe this is, y equals 2 or something. If I plug 2 in there, I get a negative number. So y is decreasing. So at this moment, y is decreasing, which means y is going down, which means we're moving down. right? Because y is the position up the axis here, and at that moment the rate of change of y is negative, so I'm moving down. But x isn't changing, so I'm moving straight down. Over here, on the other hand, maybe I'm at a quarter or something. If I plug a quarter in there, or if I'm at this point and I plug 0 in there, I get a positive number. And if I get a positive number, then y is increasing. And so we're moving upwards. So if I'm sitting on this green line where x equals 1, if I'm above the equilibrium point, I'm moving down. And if I'm below the equilibrium point, I'm moving up. Let's go to some point over here and think about what happens. If I'm sitting at a point over here, what happens to x? And what happens to y, right? So at this point, x is bigger than 1. So if I go over here, x is bigger than 1 because I'm above the line. Sorry, x is bigger than 1 because I'm to the right of that line, x equals 1. And y is bigger than a half because I'm above the line, y equals a half. So if x is bigger than 1, then this is going to be negative. For example, x here might be 2. If I plug 2 in, I get a negative number. So the rate of change of x is negative. Sorry, the dx dt is negative. The rate of change of x is negative. If I plug in a number bigger than 1, this quantity is negative, so x is decreasing. If x is decreasing, then I'm moving to the left, because that's what it means for x to decrease. If y is bigger than a half, I plug in a number bigger than a half, then the y value there is, the value I get there is negative. That's the rate of change of y. So the rate of change of y is negative as well. So if I start at this point, x is decreasing and y is decreasing. So I don't know exactly what's happening here, but I know that overall I'm moving down and to the left, right? Because x is decreasing, so I'm moving to the left. Y is decreasing, so I'm moving down. So my overall motion is given by that yellow line. Let's flip it over here and think about a point up here. Y is still bigger than a half, so over here dy dt is still negative. Right? Y is bigger than the half, I plug in a number bigger than the half in there, and the rate of change of y is negative. But dx dt, in this case, x is now less than 1, for example this might be x is a half, and that's going to give us a rate of change of x that's positive. So at this point y is decreasing, but x is increasing, and so my overall motion somehow is down, because y is decreasing, but to the right, because x is increasing. And I can continue that game in each of these little quadrants because these are linear factors. The only place they change sign is at the, when we cross these lines, when we cross y equals a half and when we cross x equals 1. So if I come to a point down here, x is less than 1, so still the rate of change of x is positive because I'm plugging a number like a half in there and it comes out positive. I'm below y equals a half, so my y value might be a quarter, and this is therefore positive. So y is increasing, x is increasing, and so x is increasing, y is increasing, we get that kind of behavior, and so my overall motion is somehow up and to the right. I continue doing that in this next quadrant. dx dt in this quadrant, now x is bigger than 1, and so the rate of change of x is negative, just like it was up here. But y is still less than a half, which means just like over here, the rate of change of y is positive. So if I'm starting at some point here, x is decreasing, we're moving to the left, but y is increasing, we're moving up, and so the overall motion somehow is like that. And so we see what happens. I can go to that other point on this curve. Imagine that y is exactly equal to a half, then this quantity is exactly 0, so y is not changing. But x is going to change. It's going to be increasing in this region, and it's going to be decreasing in that region. Right? Because in this region, dx dt is negative because x is bigger than 1. In this region, dx dt, drew that badly, dx dt is positive because x is less than 1. And so with all of those things together, I can draw typical solution curves. Because imagine if I'm on this line, then I'm moving straight in towards the equilibrium. There's my two lines. I'm moving straight in towards the equilibrium, and the things I've been drawing give me directions, right? I'm moving up or down depending on whether I'm above or below. I'm moving in from the left and the right. But if I'm at some curve up here, then they all have to be going down and to the left. So the curves, I don't know exactly what they look like, but they have to somehow be going down and to the left. Maybe there's one right in the middle that goes straight in. Maybe there's one that looks like this, but they're all going down to the left. The ones up here have to be following the general sense given by that yellow line. These ones have to be going this way. these ones have to be going this way. I don't know exactly what they look like, but I know that these ones all go to the left and up, and these ones all go to the right and up, right? And so all my curves, these are the solution curves, and these things are called trajectories, right? There we go. So these blue curves are called the trajectories of this system. Trajectories, or they're also known as orbits. So they're literally the solution curves. They're the values of x and y. So you can imagine if I start with some initial value, if this is my initial value, then this curve tells me what's going to happen. If I start with an initial x value here, there's x0, and an initial y value there, there's y0, then I'm going to follow that blue curve. So I'm going to move up and to the right, and the only place I can go is that equilibrium value. So this equilibrium is stable. It's stable because no matter which direction I'm coming from, I'm moving in towards that equilibrium value. So that's a stable equilibrium right at the center here, and you can see roughly how these trajectories or orbits behave. And the other thing to mention here is that those arrows represent time. You know how I was drawing these nice little arrows here? Those little arrows are what's happening with time. So the arrows represent the flow of time. To be more precise, they represent an increase in the t variable. So as the t variable increases, and I'm usually going to think about it as time, I follow those curves in the direction that the arrow points. Because the arrow is coming directly from saying, what's the rate of change? So the rate of change is telling us how x and y are changing as time increases, as t increases. And so we see time on this picture. Even though it's not an axis, we don't have a t-axis, the arrows represent motion in time. So starting from an initial value like this one, we then in time will flow towards that equilibrium point. So our analysis of these autonomous equations suggests that all of our any initial point we choose will eventually end up heading in to that equilibrium point in the middle there. This example really covers all of the big ideas in the section. So let's do another example to see how these things work. The main difference with this example is we have a set of nonlinear differential equations. So they're still first order. First order means just first derivatives appear, and they're still autonomous, which means there are no t's in the right-hand sides here. But this is nonlinear because it includes terms like x times y. So it's not just, like our last example, it's not just a function of x and a function of y that's entirely linear, that's just a straight line function if I were to sketch it. These are nonlinear because I'm multiplying x's and y's together. And that could include things like x squared or sine of x. Any of that will make it nonlinear. So our first job in all of these is always to find the equilibrium points. And we just do that by setting the derivatives to 0, right? And so that gives us two equations to solve. So let's look at each of them. In fact, I'm going to factor them because notice I can pull an x out from that first one. So this is x times 3 minus 2y. And from the second one I can pull a y out. This is y times minus 2 plus x. And so the system I'm going to think about solving is the factored form over here. And in fact, I'm going to take that first equation. So we've got two equations to work with here. Take whichever one you like. The best way to look at it is look at equation 1, for example. I could do it from 2. But the best way to look at it is look at the options. From that first equation, either x equals 0 or 3 minus 2y is equal to 0. So those are my two ways of solving that first equation. These are multiplied together. When I multiply them together, I get 0. So either x is 0 or 3 minus 2y is 0. If x is 0, then what does 2 give us? Well, looking at equation 2 and plugging in x equals 0, I get 0 equals y minus 2 plus x, which is 0. And so that tells us that y is 0. Because the only solution here is, this is just minus 2y, and so y is 0. So here we've got the solution, the equilibrium point, 0, 0. On the other side here, I had this second factor being 0, and this is always the key, factorize it. The second factor is 0, so that means that 2y is going to be 3, so y is 3 halves. So there's a value for y, and then what does equation 2 tell us? Because this or this independently solve equation 1, so we're done with it. Now we look at equation 2, and equation 2 tells us that 0 must equal to y, which is 3 halves, minus 2 plus x, and so the only solution for that is x equals 2, and our other equilibrium point is the point 2, 3/2. And this is typical of what you will see when you have nonlinear autonomous systems. You will have a system of equations to solve for the equilibrium points, and in this case we get 2. So let's have a go at sketching the solutions of this system based on the arguments we just made and the fact that we know the equilibrium points. Okay, so let's have a look at this system using the information that we built. And notice that I've drawn the equilibrium points here, and I've marked some special values here, some x and y values. And those values are special because they make individual terms in these equations equal to 0, right? So this is the line y equals 3/2. When y equals 3/2, x isn't changing. Also, when x equals 0, well, that's the y-axis, x is also not changing. Because if I plug x equals 0 in here, the rate of change of x is 0. And then this line, where x equals 2, y doesn't change. Also, the line y equals 0, which is the x-axis, also is a line along which y is not changing. So those lines are special. And what we're going to do is look at the regions in between them. So for example, let's think about a point in this region. So x is between 0 and 2, right? So what happens to x when we're between 0 and 2? What's the rate of change of x? Well, when the x value is between 0 and 2, so the x value is positive, so this term is positive, and then this other term, the y value is bigger than 3/2, so maybe it's 2. We're up here at y equals 2 maybe, and if I plug y equals 2 in there, I get a negative number. So this is a positive times a negative. So x is decreasing in this region. What's happening to y? Well, in this region, again, x is between 0 and 2, so maybe it's 1. If I plug 1 in there, I get a negative. The y value here is positive, so this is also decreasing. So y is decreasing, x is decreasing. The overall motion in this region is down and to the left. And then we go through and do this in every region here. So the key thing in this piece of the region, right, there's y equals 0, x equals 0. X and y are both positive in this region. Those two are positive. So it's these terms that determine what's going on. So for example, x was a half in this second one. Sorry, not a half, yeah, okay. So x is a half in this second one would make the rate of change of y negative, and so y would be decreasing. Now the y value is less than 3/2, so maybe this is y equals 1. If I plug y equals 1 in here, I get a positive out. We know x is already positive, so x is increasing in this region. So the overall motion here is down and to the right. And then we can keep doing that. In fact, we've already done a bunch of the calculations, right? Because we said if the y value is between 0 and 3/2, then x is increasing. So x is still increasing in this region. But if the x value is now bigger than 2, then y is now a positive, and so the rate of change of y is now positive, and so we're going up. And so in this region, we have a picture that looks like that. And I'm going to go through in each region and do the same kind of calculation. If x is bigger than 2, then this, and y is positive, then this whole term is positive. So y is still increasing in this region. But now the x value is positive, and the y value is bigger than 3/2, and that means like y equals 2, for example, and that will make this negative. So we'll have a positive and a negative, which makes the rate of change of x negative, which means x is moving to the left. X is decreasing. Okay, so there's our little thing here, and our overall motion is to the right. What happens right on those lines? What happens here? What happens at the point where x is exactly 2? When x is exactly 2, y is not changing. So it's a pure motion in the x direction. And if you work out what that motion is, because y is bigger than 3/2, this is going to be negative. And so our motion is entirely to the left there. It'll be entirely down here. Well, let's go over here. Again, when x is equal to 2, y is not changing. But now the y value is less than 3/2, so this term will be positive, and so x is increasing. When you make the same arguments here, we're going to get x decreasing. Over here we're going to get, y decreasing. Over here we're going to get y increasing, because if y is 3/2 along that straight line, when y is 3/2. X isn't changing because this whole thing is 0. And then it depends whether x is bigger than 2. And if x is bigger than 2, the rate of change of y is positive, so y goes up. And if it's less than 2, the rate of change is negative, so y goes down. You can see how that works. What about if x is equal to 0? If x is equal to 0, then this quantity here will be 0. And so x isn't changing. It's a pure change in the y direction. X is 0, so y is decreasing. So along this curve, when x is 0, we're moving straight down. What about when y is 0? Well, when y is 0, this term will be 0, so y is not changing. The rate of change of x, though, will be 3 times x. X is positive, and so we're moving to the left. X is increasing now along the curve where y is equal to 0. Right? And so we get a pretty good picture. We could do the same in these regions where everything's negative. I'm just going to imagine for now that I don't care about those regions. But we could do the same thing over here, right? We could say x is negative and y is negative, and we're in, below y equals 3/2 and above y equals 3/2, because we change going through that curve. But in a lot of our problems, x and y will represent positive quantities like populations or financial values, and so we're not going to be so interested in the negatives. But we could extend this analysis into the negative values. So if you think about what the curves look like here, somehow the curves must be doing this, right? The solution curves must be going and circling round, because you can see there's a flow here. There's a circular flow going around these points. If I'm really close to the edge here, I expect the flow to look kind of like this, right? Because I can't cross these lines. This is literally, think about it like a fluid or something flowing. If I'm close down here, then I'm moving to the left. But if I'm a little off the axis, then I'm moving up as well as to the, sorry, that's to the right. If I'm down here, I'm moving to the right and up a bit. So as long as I'm not on the x-axis there, I'm always going to be increasing a little bit. In the same way here, these are always going to be decreasing a little bit because we're always moving down and to the right. So all of these, this represents a circulation around the what's this? This is the equilibrium point. This is the equilibrium point at 2/3/2. And so I can't really say whether it's stable or unstable, because I don't know whether, so there's possibilities here, right? Imagine me completing one of these curves. It could look like that. It could be a perfect circle. That's a possibility. We're circulating, what's that, counterclockwise in a perfect circle. Or we could be spiraling. I don't have enough information here to know that what I've got isn't a spiral. It's spiraling outwards the whole time. I also don't know that it's not a spiral that's going inwards the whole time. All of these curves are anti-clockwise, but this could be a circular or a flow that repeats, and this could be a spiral that could go in or out. And I don't know, it doesn't even have to be circular, it could be an oval, but looping around again and again. So I don't know which of those it is. My analysis here isn't enough to tell us. We can use Mathematica to see a bit more of what's going on. So let's have a look what Mathematica does for this particular example. Okay, so here's the Mathematica code that implements this system of autonomous equations. And you can see, it went away, you can see the equations entered here, and they match the differential equations we've got up there. And all I'm doing is using Mathematica's numerical solver, this ND-solve program, with the differential equation and different initial conditions. So I'm starting at the point 1,1 and the point 1,3 and the point 1,5, and I'm building a trajectory based on each of those initial conditions, including that equilibrium initial condition 2/3/2. We know that's an equilibrium point, so we should stay right on that point. And if I plot these, and I'll put this notebook on Mathematica for you to look at, if you plot these, here are the trajectories you get. If you look right in the center there, if you've got good eyesight, you can see that equilibrium point at 2/3/2. So 2, 1.5. That's an equilibrium point. The dot sits there for all time. But other than that, we just sort of circulate around these points, and you can see the general shape. They're not circles. I expect to be getting curves that are coming down here and then flattening off and then rushing along this way, and then eventually they're growing, and eventually they're going to go up. Sorry, they can't go up yet. It's got to be going straight up when it crosses this line, just the way it's got to be going straight across when it crosses that, and straight down when it crosses that. But now it's going to start bending around, and it's got to be going straight again here when it crosses that one, so I haven't drawn it very well. So this is a general idea of what the things look like. And they're going to get more, the further I go out that way, the more they're going to come back sort of like this. But this gives you an idea of what the picture, what the solutions kind of look like. So they're not circles, but they are definitely looping. It looks like they're definitely in trajectories. And the 0, 0 equilibrium point there is unstable because we move away from it. If we come down here, we then spin around and go off to the right. So I never get to that equilibrium. This one is neutrally stable. So this one, because we don't really move away from it, but at the same time we don't move towards it. So we're kind of neutrally stable. We just kind of hang out in that region. All right, so this gives you an idea of what these look like. Have a go at some problems. Come talk to me in office hours if you get stuck. There'll be some like this on an assignment pretty soon. I'll talk to you soon. Bye.